All right, excellent. This will be a lecture that involves more advanced features of finance and mathematics. Luckily, there will be no big surprises from a Python point of view. So I hope you will accept this challenge, as it will be a great way to apply what we've learned in practice. We will import everything we have used so far: NumPy, SciPy, Pandas, and Matplotlib. This time, we will compute the price of a call option in a more sophisticated way regarding the previous lecture. To compare the two approaches sensibly, we will use the same data and will base this analysis on Procter & Gamble for the same time period, starting from the 1st of January 2007 until today, the 21st of March 2017. Again, we will be interested in the adjusted closing prices. Okay. Since the behavior of a single stock throughout a given period is of interest, estimating log returns will be appropriate. All right. What is so special about this approach? The method and the formulas we will apply to compute the call option price are different. Earlier, we used the standard formula for calculating the price of a call option. However, as a financier, you would like to run thousands of experiments to be sure the price you pick will be the most accurate one. Monte Carlo simulations can provide us with thousands of possible call option prices. Then, we could average the payoff associated to these randomly generated values and discount it back to today. The trick lies in the formula we will use to calculate the future prices. It will be another version of a Brownian motion, an approximate formula, and the approach employed will be called Euler discretization. There is a large amount of literature on this topic, and we need not know the whole derivation by heart to take advantage of the formula. Here is what it looks like. The stock price at day t equals the stock price observed in the previous day, t minus 1, times e to the power of the risk-free rate, r, minus half the variance of the log returns, multiplied by a fixed time interval we will call delta t, plus the standard deviation multiplied by the square root of delta t times a random component, z. Let's go through several steps that will allow us to assign values to the variables in this long formula. The first thing we'll do is assign a risk-free rate to the variable r. In our previous lectures, we used 2.5%, and we'll do the same thing here. Next, we can obtain the standard deviation of log returns and store it in a variable called stdev. We immediately check its type to verify whether it is a series. We intend to use it in array operations afterwards, so it is necessary to turn it into an nd array by using dot values again. It is a neat trick to store the new object into a variable that carries the same name. So, after we run this cell, we will have stdev as a NumPy array. Great! We'll have the same time horizon, 1 year again. We are forecasting prices for 1 year ahead, so the number of the time intervals must correspond to the number of trading days in a year. We will assign to this variable the value of 250. Now, we can create the fixed time interval component delta t, assigning it to the fraction t over the number of time intervals. Okay. Next, how many times do we want to simulate the random component z? When we forecasted future stock prices earlier, we chose 10 times, right? We can choose a much larger number and then project on the graph only 10 of these outcomes. So, why not pick 10,000? We can definitely do that. That'll be a piece of cake for Python. The random component z will be a matrix with random components as drawn from a standard normal distribution, which, as already mentioned, implies a normal distribution with mean 0 and standard deviation of 1. The dimension of the matrix these values will occupy will be defined by the number of time intervals, augmented by 1, and the number of iterations. Great! Finally, you are well acquainted with how we can create an empty array S of the same dimension as the random component Z. The zeros-like method allows us to do this easily. And to fill its first row with the last available stock price data for P and G, we could use the iloc method to extract the value from our data. Okay. So, besides changing the formula, which differs from the one we used for calculating future stock prices a few lessons ago, the rest is almost identical. We loop from 1 to the number of time intervals plus 1, and we create a whole stock price matrix with a dimension of the time intervals plus 1 to the number of iterations. More precisely, 250 plus 1 equals 251, and we have 10,000 iterations, so the dimension of this matrix is 251 to 10,000. To plot only 10 simulations, we can use a matplotlib trick. After we specify we would like to plot S, we could add an index operator, where we designate all the 250 time intervals that must be plotted by typing a colon before the comma, and then, since we are not willing to see all 10,000 potential tracks, we can limit the graph to the first 10 we have generated by writing :10. Okay, our simulation is complete. Let's take a little break and come back for the calculation of the call option's price. See you in the next video.